to host Professor Rohan Paul. He is an associate professor at the Department of Computer Science and Engineering at IIT Delhi. He works in the areas of robot learning and human-robot teaming in the context of autonomous manipulation. He received his BTech and MTech from IIT Delhi and DPhil degree at Oxford University, UK, and was a postdoctoral researcher at Computer Science and AI Lab at MIT, USA. His research has received Best Paper Awards or nominations at RSS 2016, IROS 2013, ICRA 2010. From whatever little I know of robotics, I definitely know that these are top tier conferences in this area. He is a recipient of 2 national awards and named one of 35 global innovators under the age of 35 by MIT Technology Review. It's really great honor. Good to hear this. His current research on intelligent robotics for human assistance supported through research grants from are supported through research grants from DRDO, ICMR, and DST in India. Thanks very much, Rohan, for accepting this offer to talk at this class. I'm sure the students will enjoy your talk. Okay, the floor is all yours.
Okay, thank you, ma'am, for a very generous introduction. And of course, I've heard a lot about your work and in general the NLP research at IIT Bombay. I also had an opportunity to come to IIT Bombay for a number of occasions, and I will always feel inspired coming to your campus and interacting with faculty members in various departments. And before I begin, I really want to remember Professor Pushpak Bhattacharya, who reached out regarding this talk, and I had a brief opportunity to meet him on 1 or 2 occasions when he had visited. And legacy of a great person will continue, and the legacy of such a person lives in the faculty colleagues and the students and the researchers that he comes across. So I just wanted to share that before I begin this talk. So we'll get started on this. And firstly, I will also mention that I would not typically be classified as a natural language processing person. So please do forgive my ignorance on certain topics. I will try to do my best in being clear and try to engage with an audience which primarily comes from NLP background. This talk is about enabling robots to understand language. And before I go further, I just wanted to double check, is my screen visible and is the screen in full screen mode?
Yes, so your screen is visible.
Okay, great. So this talk is about enabling robots to understand language. And my understanding of the field has come from the requirement of creating machines that interact heavily with humans, and all the work that you will sort of see is geared towards that. And as you would sort of see today, there are a number of developments happening at the intersection of various fields in AI. And this is one example, as you will sort of see, of how autonomous systems, also called embodied AI systems, interact with NLP kinds of concepts and the interlinkages between the two. So I would really call myself more coming from an embodied intelligence perspective, but I will highlight the importance of understanding language and language models and those aspects and the impact that is having in our area. That is one part of the presentation. The other part of the presentation is a little bit on the technology side to see how does one relate core ideas that you may have studied in your course, in an NLP course, and how do they relate with dealing with physical systems. So I think that would basically be my hope for the remaining 1 hour or so that we'll have some interaction with, and I'm happy to also hear from you about your thoughts and any questions you may have. So let's begin somewhere. And this is a brief outline of how I'll be structuring today's conversation. So we'll first build a little bit of a understanding of the domain in which we are going to communicate with machines through natural language. We'll set up a little bit of a model in which we will see the role of language. And then we'll see some efforts in order to bridge this gap between natural language understanding and the needs for embodied AI systems or AI agents. And finally, I'll bring together some of these ideas as saying that the natural language understanding today in this area is also interacting with perception as well as action. And that's where I'll sort of a little bit talk about where I see these commonalities getting strengthened in future research. And to set the context, this slide is emphasizing historically how humans have been interacting with the physical world. If you go from the very top downwards, here you will see uh, essentially different ways that humankind has invented tools in order to manipulate or interact with the physical world. So you start from the agricultural age where there was a plow, and the plow helped in increasing agricultural productivity, following which there came an industrial age when there was an engine. The steam engine modified locomotion and transportation, as well as the steam engine, helping in factories. And that again led to development of society in a certain way, improving productivity, industrialization, so on. And all of us are familiar with the fact that computing has had a very fundamental impact on our society. Each one of us carries a computing device. We interact very heavily. We study their inner mechanisms. And clearly, the kind of computation available per person has significantly gone up if you trace back the last 50 years of technological development. And if we try to extrapolate this further, where we are going in some sense is the all pervasive, or the influence of AI, but also when AI starts getting into physical systems. Systems such as, let's say, Alexa, or various kinds of sensing systems, but also, let's say, the robotic systems, which are essentially systems that are interacting or exchanging energy with the real environment or the real world. And what we see from top going down is the ability to affect the environment more and more. And that's the progression we are seeing, and that's the progression which is going to continue. And the age of intelligent machines essentially offers that, that in the future, that one should be able to interact with the physical environment and take that, manipulate the environment to our objectives. Now, if you look back at the word robot or robotics itself, that does bring together various different kinds of visions. We think of robots in a variety of ways, right? So I would basically, from an AI point of view, describe the robot in a slightly different way. We'll say that on one side, we have cognitive intelligence, which is the ability to understand high-level constructs. And on the x-axis, in some sense, this is time, or this is how the things are developing if we observe a robotic system more from an AI or cognitive perspective. So the first robots that appeared are essentially mechanical tools which can perform fairly dexterous manipulation. They can be precisely controlled. And there's a lot of beautiful theory that has been developed in mechatronics, in mechanical engineering, as well as in control. And IIT Bombay is really known for control. These all different machineries coming together are making essentially easier for machines to interact in very precise ways with the environment. And hence you see applications like Da Vinci is one example, but many other precision-oriented robots used in manufacturing and many others fall in this kind of a category. But in terms of intelligence, this is one form or a basic form of intelligence where the machine is being continuously being controlled and precisely monitored by the human operator. So you see the human operator here, who's in a tele-immersive kind of a system and is very precisely guiding. And what the machine is doing is to essentially remove the uncertainty in these movements and making them very precise and then operating on the side. But the human is engaged in a pretty detailed, almost part of the control loop. The human is operating very closely with the machine. Now, from here on, things have moved towards remote operated machines, or remote control robots, which essentially are operated through a teleoperation system, but through a tablet. Maybe you draw that the robot should move from this point to this point, or there's like a point and click kind of a mechanism where you click in a particular goal location and the robot starts moving in that direction till it finally reaches. And a number of, so each, many of us would have seen robots being controlled in this kind of a mechanism, where there is now a little bit of a separation between the human and the machine. And you're controlling that through a distance. And remote controls, joysticks, these are essentially ways of point and click. These are ways to interact with this machine. That means that with sparse control inputs, the machine needs to interpolate its own motions and physical interactions in order to really satisfy the objective which has been specified by the human operator. And so that takes us from, say, mechanical oriented tools to something which is remote controlled. But where is this going in future? Now, if you imagine all the developments taking in AI today, ranging from perception to multimodal understanding through large language models, etc., if you fuse or if we infuse AI into these systems, they can start leading to very intelligent robot systems which can almost start functioning like a teammate. Now imagine that for a, let's say, a security kind of an application, we would like a machine to be doing some kind of a remote exploration for us. But what if I can talk to the machine almost as if it's another human being? For example, robot examine if the crate is empty. And then the robot responds back saying, no, I can see that there is some kind of a hazardous object which is lying there. Now we do this all the time now with ChatGPT, right? So that kind of interaction is today become possible. It was not the case just a few years ago, and there's much more which is going to happen in this kind of a space. So now you imagine that instead of this kind of a large model lying inside a computer or running on a server, what if this could be on a system which is physically and moving around and interacting with the physical environment? So that's the future that we are looking at. It's the future in which more of human machine teaming is going to happen. Why? Because the machine itself will start operating at conceptual structures and be able to understand high level concepts, which is sort of required. And that's where we are going. And that's where the entire field itself, there's significant progress moving in this direction, right? So increasing general purpose intelligence and being able to operate at fairly high level and only intermittently interacting with the human being as and when which is required. And if we imagine this kind of a world in which the machine or the robot is our teammate, natural language becomes an intuitive way to communicate. Humans as a species have developed language. It has a variety of functions, but some of these, one of the main functions is communication of ideas. It is sharing knowledge with each other. And in some sense, as a civilization, we write down things which we pass on as knowledge to the next generation. So language is really, really special. And if these machines are to operate in a very natural way, then we need these machines to be able to respond to instructions as has been given here. So let's say I have a home support robot and I want to say, prepare my breakfast, and I want this for breakfast, and maybe the machine understands that and is able to autonomously then synthesize a plan in order to execute this. See this example. This is from the Bajaj factory where an assembly kind of an operation is going on. And you see a robot arm, which is picking and placing and handing over certain parts to the worker who's commanding. And what if you ask the robot to engine ke bhago ko ikhattha kare? Right? So some assembly is going on and you want some parts to be brought in, and the machine should be able to respond to that and provide that, right? And so on and so forth. In hazardous space exploration or hazard prone area exploration, there are a number of examples in which you would like the machine to be commanded to go to a certain area and then tell us what lies there and what objects are there, and before the human actually goes there, right? So the critical problem statement that we are going to come towards is to actually do this, that how does the machine take in a language instruction and figure out what is intended by the human partner. And the reason for doing that is that once I understand the intent, I should be able to break that objective down into smaller and smaller instructions and actually execute the entire chain of actions in order to satisfy what was intended by the person. Okay, so what we're really talking about is the human communicates at a high level through an instruction. I would like to extract the intent. I would like to ground that or associate that with the existing environment or the world state, perform appropriate reasoning and planning, and then finally execute the behavior to satisfy the human's intent. So that's a problem statement, right? And what's slightly different from, let's say, a pure NLP kind of a setting is the fact that the machine lives in the real world. That means it needs to look around, it needs to understand what objects are there, what regions are there, and what all is there, what is not there, etc. And that perception as well as action sort of comes in. Because finally the machine is going to interact. So how does it synthesize its actions, planning, all of those aspects come in, something that comes very naturally to us. So this is not something which is very different. We do this all the time. But having these cognitive processes algorithmically built in through learning and many other aspects is where the real challenge is. And as engineers, we model problems in a very formal way. That means we make diagrams and we understand things from system point of view. So this is one way to understand robot as a goal-directed agent. So AI talks about agentic view of an AI system where there's an agent that's interacting with the environment, collects observation, and we can think of the robot exactly in the same way. With a, just to draw your attention, there is a human, which we are going to explicitly write down. The human communicates an instruction. This instruction is to be understood in the context of the environment state, the world state here, and then a plan is synthesized. And we're going to talk about this as a plan because it's a sequence of high-level actions that picking, placing, moving, pushing. And we assume that there are low-level control loops which are available. And this is where all of control line of work comes in, where each of these actions is going to be executed. I'm going to be focusing on the intelligence aspect, on mostly focusing on this part, assuming that the controllers are available and they are reliable and they can sort of recover and do some kind of disturbance compensation. Now, given this view, we can think of a robot essentially as a function. And that's something which is important. All that the robot is doing, it's a function f, let's say parameterized by theta, which essentially is going to take the instruction from the human partner, is going to understand the world state. Maybe it has some prior knowledge or background knowledge as well, and is going to synthesize the plans which are going to be executed. Now, what we want from this function is to be able to respond to a large number of goals, of diverse goals being given in natural language, and it should be able to perform all of these things. And that bears resemblance to something like multi-goal kind of settings, which are very common in AI. So you'll be giving a goal from natural language. The robot should be able to understand that, synthesize, plan, and then go there. And what we really want is high goal reachability. That means that if I execute the plan, I have a high, high confidence that we are going to reach the goal state, or we're going to accumulate a high reward. So if you're familiar with fundamentals of AI, we can think of this as an agent operating in a Markov decision process, which is one kind of a formulation. We can make it more complex as well, but more formally, it's essentially a goal condition Markov decision process in which the world is a state. The agent is given a certain goal. It needs to take its actions. The actions are uncertain, and so on and so forth. Right? So that's the underlying formulation. We're not going to reference too much, but just to sort of see that this connects back to fundamental AI representation of agents. All right. So now with that kind of a background, let's take and let's start building this kind of an agent from first principles. And say that how do you build a machine that can take some high-level input and then produce a high-level plan corresponding to that instruction. Now, in order to do that, okay, where do we start? We first start with endowing the machine with some kind of a primitive skills. Just as we have skills such as picking up something, placing something, walking, etc., the machine needs to have some kind of behaviors, some kind of a primitive skills which are available, which can be adapted and can be sequenced. So what you're seeing here is a robotic platform. This is a ground vehicle with a manipulator on top, which is doing picking of objects on the ground. So this is picking from the ground. This is picking on top of another object. This is picking from inside another object. And correspondingly, you have placing. And these are various kinds of placing. Placing on the ground, placing on another surface, placing inside another object. Right? So what I want to emphasize here, these are primitive skills, but they're adaptable. They can adapt based on the supporting surface, what you're putting this onto, whether you're putting that in a confined surface and confined area, etc. It can adapt to that thing. But these are very short horizon kinds of tasks. This is essentially just picking of an object. but we want to do more. We want to essentially clear an area, or we want to make an assembly, etc. And that's where some ability to plan or to chain these actions is going to come up. And most of the time, human language conveys higher level tasks. Like I may say that clear all the objects on this table, or clear my room, etc. Those high level things obviously require many steps to be performed, various number of actions to be performed. Now, in order to do that, there is a certain way of encoding these actions so that some planning can be done. That means these actions can be chained. So what you're seeing on the right is what is called a PDDL kind of a representation, which is capturing when a certain action is possible and what are the effects of that action. Okay, and this is very classic 101 kind of an AI. Today, this gets replaced by other things like learned behaviors, etc. But this is essentially talking about the fact that you can pick something up from one area, and when you pick some object up, it moves in your hand, and then you can place it in some other location, and wherever you picked up the object from, that is now clear of that object. It captures things in logic, right? And with that, you can start chaining actions together, because you know when actions are possible, when actions are not possible. So on the right-hand side, you're seeing the chaining of actions taking place. I just fast forward it this way, where the robot wakes up, it starts observing what objects are around, and it makes a certain map of which objects are present, like a pipe or object on top of another object, etc. And it records, and it will also speak back to the human operator that I see a pipe, I see two blocks, one is stacked on top of the other. And so it knows this kind of semantics, and that's sort of being built in. And then it starts, we can ask it or command it to perform a clearing option. For example, here we are saying that clear all the objects in front of the robot. So it moves its hands, it grasps a certain kind of an object, puts it somewhere else, and it will continue to do that till the entire pile is cleared. So this is a demonstration of clearing a pile or clearing a set of objects in front of the robot, and it will continue to do that. So it's able to ground that instruction into these objects, and then it'll satisfy that. And here you're seeing the grasping and the entire pipeline running, which is doing the control part and various other things that go on into the physical aspect. But it's essentially going to chain that. So it does one object, then it does the second object. It picks up another one, puts it on the side, picks up another object, puts it on the side, picks up another object, and here you see a little bit of adaptation. Like pipes are a little bit difficult to pick up, so it has to adapt its motion routine a little bit, figure out a collision-free path, and then do the other part on top of that, right? And finally, it'll finish the task, put it on the side, and then report it that I have actually cleared this entire area. So clearing requires understanding of regions. So there is a geometric representation of regions like front, back, left, etc., and that's how it's able to understand this instruction. Again, you're seeing this from and another experiment. This is in an indoor environment where the
objects in front region.
Yeah, there's audio also. I don't know whether that played, but the audio was saying that I'm going to scan the front area for objects. So like a child, it's moving around, and this is a live view from the machine. And the machine is saying, well, I see these objects. So it'll respond back, and it'll tell that I find these objects, and it'll populate that in its world. So it said that I see a pipe and I see this box in front. It tells that to the operator, and then the operator will say, clear this area or pick these objects up. So if you say clear the front area, this entire instruction will get broken down into smaller pieces, like pick up the case, put it on the side, pick up the pipe, put it on the side, and the robot will start executing that plan. Now, this is the real execution going on when it's responding to the first part of the instruction. It will pick it up, establish the force closure, move it around, and then happily sort of complete this task. But the point which is worth mentioning is here that this is the planning view, that as this is the live view, and then the instructions get broken down till it'll finish this task and also report when it was successful and not successful. So it's almost as if it's on the radio, right? So on the radio, you can speak that what you see in front, finish the task. If something falls from the hand, it can also communicate back because it has this higher order semantic representation, which is there. So this gives a little bit of flavor of what all is achievable when you start talking or communicating through natural language with machines in a certain way. This is a closer look of the brain of the machine in terms of it gets a high level instruction. Let's say clear the front. It breaks it down into smaller pieces. This is part of planning, and then the entire thing start getting executed. So if you ask the machine as to which action you're executing, it will say that I'm going to actually I'm going to grasp this particular object, and this is what I'm doing. Because it has this awareness. It has this awareness that there are these modules or action routines that it's actually executing that. So that's about from, let's say, a little bit motivation side as to what kind of a systems are achievable when you can command a robot through natural language. But now let's sort of go a little bit deeper in terms of a little bit of theory, or let's try to say, understand what this problem really is and how do we understand this mathematically in the language of, let's say, models or graphical models in some sense, right? So the first thing to understand is, what is language understanding, right? What do we really mean by understanding language? Is it just a receipt of an instruction, or is it more to it, right? And the examples before should have elucidated that it's actually more than that. It's not just receipt of a language, but understanding its constituents, understanding what goal is being implied, and then figuring out the specific sequence of actions that needs to be taken. And that's what makes it different from just semantic parsing. It's much more than semantic parsing, not just semantic parsing, but semantic parsing is one part of it. So the question is, for this problem, what are the endpoints? We want to go from the human representation of a language, which has semantics, to a machine's representation. And machine's representation lives in the sensor space. So here you're seeing a LiDAR mounted on a robotic platform, and sensors is how a robot would actually see the world. So this is the world of a machine, right? Point clouds and objects and a little bit of geometry. That's the world in which the machine lives. The machine does not live in the world of language. But humans think of the world in higher level ways, right? We can say, pick up the apple or follow the road to the park, right? These are fairly symbolic entities or higher order kinds of entities, or something which has a certain macro level manifestation. And typically one can think of these as symbolic, or I would also call it in the modern way as representational, that it does have a certain semantic representation. And the whole problem is that in enabling humans to communicate with machines, we have to bridge this gap between the symbolic world in which we live, or the higher order world, and the real world in which the machine lives, which is continuous, which is noisy, whereas this one is in some sense discrete-ish, right? I will not call it purely discrete, but discrete-ish because of representations, right? But they have semantics and they carry semantics. And somehow you need to connect all of this. And that's this classic problem, which in AI literature is called grounding, which you can call it as language understanding. But that's what we are really doing. We're bridging this gap between these higher order floating things and what is the machine's own representation, right? So what we need to figure out is a factor, or say some kind of a learning construct which can connect these two. Given this, we can predict this, or given this, we can predict this. If we have that kind of an association or correlation through any kind of learning architecture, we have a system to understand language, right? So that's what we really care about. Okay. And if you look back at the history of robot instruction following, there were a number of developments. The earlier developments all relied on doing the NLP part and then doing the robotics part. That means that you take it through the standard NLP pipeline of doing dependency parsing, extracting the semantic structure, doing some kind of a part of speech kind of a tagging, extracting the verbs, and then grounding that. So that was one era, Chen and Mooney and many other lines of work, which was essentially doing the NLP part separately and then doing the robotics part separately. Right? That's a traditional way of building systems. Then around the 2011s, new ideas started coming in to say that we can't be reasoning about the NLP layer as devoid or separate from the real world, right? And to understand that, one can visualize, let's say, an example in which you say that, pass me this bottle of water, okay? Or pass me a bottle of water. And maybe there are multiple bottles of water, right? And maybe you say that pour the water from this bottle onto a cup, and maybe there are multiple cups, right? So whenever you have multiple instances of objects, it is it requires some kind of a contextual understanding of the world in order to interpret what really is being communicated through language, right? So it's not, sometimes it is possible to have this kind of a separation, but most of the time, and I'll argue as we go along that most of the time these two things are coupled, right? So the first idea that came in borrows itself from probabilistic graphical models, which is to think of language and things in the world as two separate sets of variables. So the language is this entire string of words, and there are objects and places and actions which are symbolic and things that get executed. And the idea was to learn this association in some way. Like, can I learn that when you say navigate, it means to move in certain areas? When I say the cone, it means something in the physical world, that this particular cone, this physical manifestation of the cone, something that you see in through the sensor, right? Those kinds of things. And the idea came that can we model this as a positive, or let's say through a correspondence variable, which is binary in nature. It says true if you associate this correctly. It says false if you associate this incorrectly. Okay, so language comes in. You want to associate this with things in the world. Let's say navigate towards the cone means this or this or this. And to figure which one of these is actually relevant, you want to solve that problem. And you model that at a macro level through this correspondence variable. The correspondence variable I would put as true to say that I want to infer the most likely configuration. I would want to estimate a posterior over the semantic objects that the instruction is referring, given the instruction, assuming that the instruction is ambiguous and noisy and all those kinds of things. It's a probabilistic interpretation, right? Now, so this is the estimation problem I want to solve. Posterior, or essentially you can say that I want to estimate the likelihood that things are true given language and the world, and I want to maximize the thing in the world which is being referenced. Now, the beautiful part about language is that it has structure, right? There's a well-known, both philosophically and through linguists and many other aspects, right? We know that language is structure. There is a dependency structure, and people have studied that. And with modern methods, it's not very clear whether it is there or not there explicitly. But traditionally, the models did rely on a certain factorization that comes from the dependency structure. So you can take the language, do some kind of a parsing algorithm. So let's say you do CYK parsing, or you handle phrases in some kind of a hierarchical and compositional way. You can convert a piece of text into its corresponding parse tree, which indicates a dependency. Now, the interesting part is that you can take this factor graph or this grounding graph, and based on the structure of language, we can break this up. Because all that the probabilistic model is saying is it's expressing certain probabilistic relationships between pieces of language and pieces in the world. And hence the same structure which reflects in the parse tree, which can be uncovered through NLP techniques, that can make its way into the probabilistic learning by informing the structure of this graph. So what this is saying is navigate to the cone means that if I infer the cone, that's a smaller problem to deal with, right? And the cone does not mean this barrel or does not mean a traffic sign, right? It means the cone as in this cone. And if you resolve this, then it becomes easier, or we can delegate the inference of the navigate part based on this, right? And if I continue this process further, I get something like this. I do this kind of a reasoning to say that this is the cone, I get this thing, and then I figure out that the robot has to actually move towards this particular object, right? So that's the dependency structure, which is to be there, right? And so this informs the model, and then the standard machinery of doing training a factor graph from data, etc., kicks in. So you do need simulated data, or you need real data of language being commanded with a machine, and then what should be the goal. So that kind of a training data is needed. And based on that, this kind of a training is possible to do, right? It does make intuitive sense that you can break this down and learn these kinds of factors separately from label data, right? And this changed a lot of things. This, for the first time, made it very clear. This is like a direct representation of the original idea that language has to be related to the real world for the machine to start operating. And there were a number of extensions, including our own, which builds on this entire idea of breaking the instruction down based on the parse tree. And then you can play with the representations quite a lot. For example, look at this instruction. This is for a ground vehicle, which is being sent for a reconnaissance task behind a barrel, right? So the idea is to go navigate to the cone behind the barrel. That means I have to understand the barrel. I need to understand what is behind the barrel, then to the cone, which is behind like that, and then finally I have to navigate there, right? And so the reasoning goes like this. Imagine this as a beam search, right? So there's this barrel, it gets understood behind the barrel is a region, some kind of a distribution around it, right? To the cone is this particular thing. And then finally, there is something that we need to talk about in terms of navigating, which is a path, etc. And within machine learning, things which are discrete is easier to handle. So we have to do something about that. So one of the developments was to treat this as relative constraints. Don't treat this as continuous trajectories. Think of these as constrained regions, and then do trajectory optimization to figure out an appropriate path which satisfies those particular things, right? So that you basically take a little bit of complexity of the real world in terms of continuous things and directly talk about goal constraints. The other advantage of goal constraints is that this can be embodiment agnostic. That means if I have a robot with a slightly different morphology or a different size, then my language understanding system a little bit is less affected. What I really need to change is my interpretation of this goal with respect to that platform and the capabilities of that platform. Right. But this machinery was really popular, and for a number of years, and it continues to inspire models. There were a number of developments that happened in terms of increasing the complexity of this kind of a system, etc. And it does work. This kind of machinery does work. Right. So there is some experiment that our team did it for one of the home support robot. So this is the human support robot from Toyota. And this is in simulation environment. This is precursor to the modern day home simulators. This environment, the robot is being commanded to go to the box or indicate to the box, go and fetch the can, pick up the can. It's able to understand these instructions. And the machinery under the hood is this grounding graphs kind of machinery. Actually, it's an advanced version of that, which was distributed correspondent graph and abstract graphs, which essentially work with this representation, but they speed it up, right? And you see the robot picking up and moving around, and you can command that in a fairly natural kind of way, right? So this is one way to address the problem, which is to leverage the structure of language within the training loop itself to inform this model of being able to do that. Now let's just fast track this to today. So in the previous occasion, this was a little bit standard NLP style of extracting the dependency parsing, but then going the probabilistic graphical models way of doing that. Now with the emergence of large language model, right, it's as if this model, this factor graph has been trained on internet scale data, right? So when you're doing things, when you're training models in the newer sense in terms of next token prediction, right? A lot of stuff becomes naturally available to you, particularly for multimodal kind of models. So previously, the graphical model was between language and things in the world, which are objects and region. Now, a modern VLM does something very similar. It has a way, it has been trained on images and captions. That means it naturally knows that this image contains these particular things. So this way of doing VLM style reasoning, which is vision language model style reasoning, is a natural factor. It is just a modern take on this thing. It's just that some of the factorization, maybe it's not even needed, or it is handled through representation, but it's not very different. Like in the modern sense, today it is not very different. I mean, you can think of CLIP and those kinds of technologies which relate images to language and annotation. It is just this kind of a model, but with a much different kind of machinery, maybe transformer-based architecture, which is connecting these two. So if you try to do this today, it's much easier. You maybe don't need to go explicitly through parsing, at least for smaller instructions, and the machine is able to do that. So this is from a lab today, where there's a robotic platform which is being asked in an assistive context to respond to an instruction like robot, hand me the tower that is on the shelf. So the machine goes and sees where the shelf is, examines what's there, and then is doing all the grass planning, and it will pick out this particular object, a towel in this case, and bring it back to the human, right? So it is looking for the towel object, and then it goes back to the human, and then puts it on the hand and sort of responding that, right? So this is in the modern ways. This is through the VLM agentic kind of an architecture where at least the reasoning part is being handled by the VLM, and then remaining is classic motion synthesis and classic planning, which is operating, right? The other advantage is, as I mentioned, in the older times, we had to explicitly train this model. We had to train that this is a barrel. I had to collect all this data. In fact, I spent many hours doing this kind of work where you have to create manually this kind of data and train it directly. Today, off the shelf, a number of human common objects that you find in the environment are already available at internet scale, right? So you don't have to train for them. So this is zero shot. So this is essentially a zero shot picking of a towel, and then human being recognized is all happening zero shot because the today's VLM models have that data available in its pre-training. Obviously, this is flaky, so this is a successful demonstration, but a number of times it does not work, and there are other things that need to be developed, and maybe some kind of a hybrid is eventually needed. But just to sort of see that in the modern time, this is how one would approach the problem. All right. So that's one part of it. And the ability that we have now with the machinery that has been built up is about understanding static things. That means pick an object and give it to me, or do something, or move to something. They're very static kind of interactions in terms of an NLP kind of context, right? But now what if I do something a little bit more interesting, because the agent is always observing the environment. And let's imagine that the robot is observing me putting a cracker box, or let's say a cornflakes box, some kind of a box on the table. Okay. So I put some box on the table, and actually there are two boxes on the table. There's one on the left, there's one on the right, right? And now if I ask the machine, pick up the cracker box that I put down on the table, right? Which one do you think the machine should do? Should it be the left or should it be the right? It'll be the left, right? Because that's the one that I put down. Okay. So in order to do this kind of instruction following, pick up the cracker box that I put down, I now need the understanding of actions, or I now need to be able to track videos and see interactions happening in a video. And my relationship is not going to be with a static image, but it's going to be with this continuous, in some sense, tube, or let's say this set of images that I will see. So in order to do this instruction, I need to make a factor graph or a grounding graph, but that does not operate on objects. It operates on object tracks. So I'm going to observe me putting some object down, and that particular track is what I'm going to do my reasoning with, right? So this system is called sentence tracker, which existed earlier before our work in the vision community, and we lifted that to the embodied sense. It's operating with the robot platform, and the idea here was to extract some kind of this. You can think of that as semantic parsing. So you do block X, put down X, Y, and human Y, right? The block that the person put down, I can interpret as finding a block X, putting down X on Y, and human Y. And I want to find the maximum correlation or things that maximally satisfy. So which track should go in here, which track should go in here, and which track should actually go in between, right? Okay, so in some sense, the higher order symbolic structure is being imposed on the lower level tubes, so the lower level interactions which are taking place, right? And you can think of that as a grounding graph of some kind, except that the representation we're now changing to videos, right? And there's a way to train that. We call this temporal grounding graph because there's a time component which sort of comes in, and then it allows us to be able to do this, right? So you'll see the same kind of a video again. You see, I put the thing down here. I put a box in, and then I say, robot, pick up the box that I put down, pick up the cracker box that I put down, and the machine is able to pick up the cracker box that I put. So the machine figures out that it's the left one, it's not the right one by running that system, and then finally able to complete the task. So it will descend down, pick up the object. It will start moving very soon. Right? It descends down, picks up the object, and puts it on the side somewhere. Put it on the side. Okay, and complete the task. So this was in the graphical model sense, right? And very recently, we did a more modern version of the same problem through today's technology, which is VLM, LLM, and that kind of flavor of technology. And I'll talk about the architecture in just a moment. But today we can advance this much further and do even higher order reasoning. Okay, so this video basically will show a person come in and put a few bottles in the robot's environment. And then somebody else will come in and say, robot, hand me the bottle that was placed second, right? And let's see whether the robot is able to do that, right? Person comes in, puts a bottle here, one, puts the second one, right? And puts the third one. And these are natural bottles. These are like standard bottles. And the person goes away. Give me the bottle that was placed second by the user. So another person comes in and says that, give me the bottle that was placed second. And as you can see, it will pick up the right bottle, right? So it picks up that particular one which was placed second and then hand back to the human. And it's observing through an hand configuration on the robot itself and is doing that reasoning and completing this particular task. Okay. And the way this is sort of working is we have a way essentially to we split the instruction into what refers to the past, what refers to the future, and what in some sense is connecting these two. So the one which goes in the past has to reason on the video. So there's a video language model which is being queried to essentially retrieve in the short-term memory the frames where the interaction actually did occur. Right? So you can convert this into question answering and say, when is the wiping occurring in the video? And it will figure out and give us a sequence of frames when this kind of a thing happened. And now the more specific phrase grounding LLMs kick in. So things that can reason with certain images and more precisely what interaction happened, grounding of the object, that responsibility is for a vision language model, which can very precisely reason on an image. Right. So today's finding was today's video language models are not that strong enough to do grounded reasoning. They still do very coarse reasoning, but we have so much of video, we have to prune it down. So there's no other way except to do this. So some kind of a temporal localization happens. Then the fine-grained spatial reasoning kicks in. And then finally, this is going to be projected into the 3D, and then the robot part, the robot execution is going to start happening. So this is the agentic architecture running from the past. This is reasoning in the past. This is connecting to this present and the object. Then our standard backward autonomous pipeline starts, which takes the object mask, goes into 3D, figures out the poses, and then the execution is going to start. The picking and placing is going to start. And you can do pretty interesting things. So let's see this example. So here you will see a wiping experiment in which there are a number of these towels are there. Right. So imagine it's like you use certain wipes to do some cleaning, and you want the robot to throw away the ones that were used, the wipes, right? So a person is going to come in and start wiping the surface. So they do a little bit of wiping here, right? And notice that one of these is used, then the second one, but there's one which has not been used, right? Which one? It's the pink one behind, or it's also the green one here, right? So then we say, robot, throw away the wipes that were used. Okay. And the robot goes back in time and identifies where wiping happened, and then it's able to take this and do this back, and it'll actually discard that, and it now does the second one. It'll finish the task eventually, right? So that's happening through the agentic thing. And the key thing here is today's technology makes it very general. This is again zero shot. We didn't actually even fine tune this on any data, but because it's seen natural interaction, it's able to do these kinds of general tasks. There's no constraint we put on the objects and the kinds of interactions, etc., etc. In the older system, this was done through a lot of handcrafted features and training only for certain classes like picking and placing. But with today's technology, it gets generalized fairly nicely to general interactions and general objects. I mean, that's the main thing which has happened in today's thing. But the factorization still stays. Factorizing what happened in the past, and then reasoning in the present, and then taking it forward, etc., is part of the story. In robotics, what also happens is partial observability in the sense that the object that I want to pick up, maybe I put it inside another bag, right? So then I need to also reason where that object has gone, and then I track that object where that thing has gone. So that kind of reasoning also is needed. And again, we have a mechanism to be able to do that in terms of tracking, right? All right. So that's about temporal reasoning. But there's one other dimension of temporal reasoning, which is quite interesting. And if you can sort of see me on the camera, you would notice that I gesture quite a lot. That means I'm speaking, but I'm using my hands all the time. And I sort of use that to emphasize, or in general, I do communicate a lot with the hands as well. And that's something which is also very natural, right? That we are used to using gestures along with language. And apart from convenience, it is also about succinctly communicating certain concepts to the other person, to the machine. So the example which is here is put all the edible items from here to there and maybe remove something else, right? So if I want to say put all these items away, right? It's more efficient to use a combination of language with gestures, and this is known as co-verbal gestures, right? Co-verbal means that there is a language which is overlaid by the dynamics of the hand itself. So let's watch this video. So you'll see a student do this. Put all the edible items. So put all the edible items from here, right, to there, and then do something. To there. Okay. And you see the camera view here. This is from the robot's perspective, which is observing this. And this is the robot's view of the objects and then the hand being overlaid. So I'll just fast forward this. So she's going to gesture. When the gesture finishes, the robot needs to figure out many things. It needs to figure out the region where the objects are. It picks out the edible ones out of from there and then puts it on the side, right? So it'll complete that plan. I'll just fast forward that in the interest of time. Right, so the robot, picks up the edible one. So it'll pick up this carrot. This is a plastic carrot, not a real carrot. It gets put on the basket. So it'll put this on the side, right? And then it'll pick up the other one, and it'll not pick up, let's say, a cup, or it'll not pick up a wipe and those kinds of things. It is going to, not interact with them. It will just complete this task and sort of do that, right? Let's look at another one here, which is similar. It's slightly more interesting. Put these items in a container with this kind of a shape, right? So shapes may be hard to describe, and here there's a kidney shaped kind of an object. Okay. Put these items in the container with this shape, right? Not sure whether the audio went through, but put these items in a container with this kind of a shape. So she presented some kind of a gesture, and there are two or three, there are more than one containers which are there. And the robot figures out that the kidney shaped container shown by the hand is this particular one. So it relies on that part for the gesturing, and the remaining is the NLP part or the language part, right? And it's able to then complete the task. So you'll see the picking of an object. I hope this video plays. So it picks up the object and puts it in this particular container. It doesn't pick up place on this container because the shape does not match. Okay, so it'll continue to do other tasks. It'll pick this up and again put that on the kidney shaped thing. Again, because this is hard to describe. I can say kidney shape, but it's also more natural to indicate these kinds of shapes. And you can do more interesting things. You can say, give me a container which is bigger than this size, or give me a container which fits into this size. All of these interactions can become possible with the gestures kind of thing there, right? And the core technology is converting these trajectories into a visual prompt, right? So can we convert all of the interaction in some way? And this trajectory, which is this time varying path that the human has taken. So a number of pieces are there. So there's understanding the hands, understanding the hand trajectories, then the timing, and how do you encode that. So it becomes essentially a visual prompting problem where you convert all that temporal information in some sense through a visual prompt, which has time varying pixels and a couple of other things. So the work really went into looking at the prompt strategy of how do you convert a physical trajectory into a visual prompt for the vision language model to process with that. And also emphasize this work from Dr. Shubhangi Nema. She's with us as a postdoc, and she's actually from IIT Bombay, from the cyber physical division. She did a PhD there, and then she's been with us for some time, and she's been leading this activity, which has recently been submitted to ICRA. Right. So very interesting, right? So this is co-verbal gestures. We're using other, the gesturing part to complement with language, right? So let's do one more thing, and then we'll try to consolidate after that. is to bring in the action of, the aspect of physical interaction directly into language understanding, right? So till now we have pieces to understand objects and doing interaction with objects. We know about videos and we can understand interactions, but what if the instruction is actually slightly incorrect? Or what if the instruction is not enough to convey or fulfill the task? So the task that I'm going to show is where a robot has been asked to clear away certain things from the table. And there are two cups on the table. And typically you would pick them up and you will throw them away, right? These are styrofoam kinds of cups. They are discardable. And the robot is told that the cups on the table are empty and you clear away the clear away the cups.
The cup on the table are empty.
And clear away the cups. I'll just turn this off. So it's been communicated, the machine is being spoken to. And what it starts doing, it says, okay, there are two cups. I'm going to throw them away. And it picks one up. And then immediately, it'll discard. So it'll pick this up, put it on the side, and it'll throw this away. Now let's see what happens to the second one. So it goes and it picks up that particular cup. It'll try to pick this up, and then something strange will happen. The machine will experience some force. There is some strain that it is experiencing, which is indicative that this is actually not empty. There might be something there inside. So it tries this again and again, because I was told that it's actually empty, right? But it's actually not. So it's trying to experiment again and again. And once it really says that, okay, this does not look empty, it's not going to throw it away. It's going to put it on the side, right? So what really happened? What really happened was that there was a small mass, some kind of a weight was kept on inside one of these, right? Which is not available. This is not a visual input which is available. So what the robot is doing here is that it's using its force and torque measurements in the hand. So it's using those force signatures and the strain measurements to do some kind of an estimation of whether this is empty or not empty. So you can assume that this latent state is a Bernoulli variable on which there's a conjugate prior, which is there, and these experiments are informing us a belief. So there's a certain belief, and this belief is being updated based on the observations. That means you pick it up again and again, you get strong strain measurements from the hand. That means that there is something inside, then I can be more and more confident. I will change my belief. I will update through my posterior conversion. I will have a posterior that there's something really inside that container, right? It's not really empty, and I should not throw this away. So it does that. Now, from the theory point of view, we can think of that as information gathering, right? Because if something is ambiguous, you can either ask the human back, or you would do your own experiments. And what you have here is a mechanism in which the robot is actually doing that experimentation, right? So maybe it has to look more and get more information, being able to do that, right? And this is another example on a different vehicle doing the same thing, that let's say you want to remove certain objects, but some of these objects could contain some other heavy objects. So it needs to do a little bit more experiments, and it's doing all these experiments, right? So it's like doing all these trials and building up a certain kind of a belief to solve that task, right? So here it says pick up the heavy case. So it has to do both, and it has to figure out which is light, which is heavy. And this is very much an embodied, unique to the embodied setting, right? Where you do some physical interaction, and these are non-visual properties, etc. So you need to really interact with the world to figure this out, right? And here these are real experiments which are going on till it will converge to the right kind of property for this, right? So I'll just fast forward. Maybe I'll skip over some of this thing and talk about one little other aspect of VLM. I do want to leave some time for interaction questions to say that I did speak about VLMs and large language models in a variety of ways, right? And one of the things that the large language models today are doing for us is that they have read a lot of text, right? That they have access to knowledge about how things are to be done and how things can be done, kind of thing, right? So one of the places where they're getting very useful is to elucidate that knowledge for planning in general, which is slightly different from language understanding, right? It's not about just understanding language, but can I think of this as like a chat GPT for the robot, where when the robot is confused or doesn't know what to do, it can go back and query chat GPT for doing something, right? And the use case here is, let's say, unstructured outdoor manipulation. Let's say that there's a search and rescue environment in which a machine has to go and it has to, let's say, rescue people, or it has to go into a disaster site and clear it away, or find survivors. That kind of a like really rough kind of a setting, right? And what happens in these kinds of settings is that manipulation is very hard. You may encounter tree branches, and tree branches don't have regular geometries. They'll be very complex. Even if you've seen many of these tree branches in simulation, the branch that I will find that is going to be very different, right? Objects can be very large. Say, for example, this broken ladder will be maybe fallen. Let's say there's a truss, which is this construction object, or let's say a broken window is lying there, right? And how do I even manipulate them is not an easy task. A lot of the manipulation till now has focused on indoor manipulation, which is indoor fairly structured objects, but outdoor, maybe objects which are broken, which are lying in odd shapes and odd angles, etc., on top of each other, they're very hard to deal with, right? So one of the efforts in our lab is around being able to have robust strategies for doing manipulation for these long-running tasks in outdoor kind of a setting. And one of the places where we got really stuck for a long time was, how do you even do grasping in this case, right? So if I have a large object, where do I start? Do I start at the corner? Do I start at the middle line? Do I just go for the center of mass? And it turns out that the heuristics are flaky. They don't really work because there's just so much which is going on in these objects in odd kind of configurations, because the pose is not constrained in these cases. And something that we relied recently was to actually take this image and ask large language models as to what do you think are the ways to grasp this, right? Um, and sort of it proposes some grasp strategies for us, right? So here you're seeing some successful picking going on, where the strategies have actually been suggested by a large model. What this model is really saying is that if you want to grasp here, that's not a good idea, because this object is in contact with some other object. But something here is okay, because this is not in contact with something else. It's likely to be stable. And in general, we know about intuitive physics, so we have some physics understanding that things in the middle is a little bit better on this thing. So there's much more detail in that system, that you do basically grasp-based decomposition of the object based on grasp possibilities, but then query a large language model to say which of these I should try first. Where do you think I'm going to succeed fast? And then do the task after that in terms of coarse to fine reasoning. So remember the diagram that I showed between symbolic and the real. It doesn't have to go in one go. It can go in stages. So you can first elucidate, okay, what can be the strategy with like options or some strategies, and those options can then be refined in a more geometric way. So here you're seeing the complete execution of a multi-step plan on the right-hand side, where these objects are being picked up and put on the side. And the task is the same, clear the debris. That's the high-level instruction given. And the robot is able to manipulate these things. Sometimes it falls and it'll go and pick it up again and do those kinds of things. But then the reasoning engine is leveraging large language models, right, for providing that common sense knowledge and doing that filtering part. And once the large language model is given some course description, then there's more fine-grained reasoning happening. Again, this video is sped up at least 2 times, right? There's some more steps happening in terms of the physical realizability or pickability is being assessed at the real time, and it's then simulating it and then figuring out where exactly it should focus, or that reasoning is happening. But again, the symbolic knowledge is being used. Otherwise, it would have been very difficult to write a particular kind of a strategy, right? So I'll just play this again. You see the clearing task. These objects the robot has never seen before. So this is completely unknown scenes. And then it's able to do that, and sometimes it works, sometimes it doesn't work. Let's say here it displays another object, it has to reason about that again. A little bit changes would happen, but at least there is some progress that it's being able to make in this kind of a thing, right? So language here becomes not just a way to communicate goals, but also to communicate high-level common sense knowledge, which is there, right? And the final piece that I'll sort of mention here is that this learning can be fairly coupled, in the sense that till now I talked about the concepts as separate from the physical world, but today modern architectures are possible, neurosymbolic learners which are possible, which can learn concepts, but also learn how to follow instructions all in the same go. right? And the way this works is something like this, that you can have an image, or let's say a task. Say, let's say here, put the block which is behind the green dice to the right of the red cube, something like this. And you see this task execution in terms of training data. This is the initial state, this is the final state. And this entire instruction is basically translating this image or this world into something here, right? So if you break this down as a program, right, we can say that all of this reasoning is going to happen. Left, right, green, red, all this reasoning is going to happen in a parse tree kind of a way. And if I write this as a program, I can start training this architecture from one to the other. So if I've seen enough instruction following examples, I can train a model to put these sequences together and then realize the final scene, because it's a transformation. And then I can use other techniques from neurosymbolic learning, which will do some aspect of reinforce for the discrete parts, and then do weight updates for the neural parts, etc. You can start acquiring representations of what it means to be a left, what it means to be a right? Remember that when I introduced spatial relation, I didn't really mention as to how these are trained, but this provides a certain kind of a mechanism to be able to do that. So here you're seeing this is simulation. The results are being translated to the real environment, but you see a complex instruction being executed through that mechanism. Put the white dice above the yellow Lego block and move the yellow cube to the top of something, right? So it's a little bit complex, but it's able to break that down. And again, the details are in the specific work, but this shows the neurosymbolic architecture works better than the pure neural approach, where the neural approach is not able to do this higher order reasoning or this temporal reasoning. It's a little bit shallow and sort of stops. And then only the first few steps are correct, and after that it gets lost in that thing. And today, fairly interesting function transformations are possible, right? So if you know the progression of the plan, that I'm going to do this, I'm going to pick a block and place it there, pick another block, place it here, all these kinds of things. There is a way to go from the symbolic succinct representation to even visualizing the plan. And that's what's happening here. The robot, even before it executes the plan, is able to visualize how the plan is going to get executed, because I can visualize that scene. And this is really helpful both for interpretability, because these are long running plans. The human needs to know what is going to happen, but also for error recovery. That what if while I make some mistake and the entire thing falls away? Can I recover back? Can I preserve part of the plan and then go back and see what I was supposed to do? And the reason I can do that is because before even I execute, I will know how I'm going to progress in the plan. And the key aspect here is this prospection aspect, that you can predict and even synthesize these images ahead of time, because you have these factors that go from the symbolic to real images. And today's technologies in generative modeling is allowing that, right? And that's how one is able to synthesize these kinds of images. So at this point, I'll conclude on the technical part and just leave out a couple of open, exciting questions, in the sense that we're still far away from being able to naturally talk to machines, right? These are still lab level experiments, or I would say early kinds of experiments in the field. But there's much more, and a lot of interesting stuff that is to be done. There are a couple of questions here on this slide, and there's one more slide on this. But I would say that one of the challenges that this line of work faces is data sets. So language data sets are, I would not call it easy, but easier to create, because it's text. I mean, somebody writes it, or you get the data from natural conversations. To get this kind of human machine data is hard, because this has to be done in the real world. And that makes it difficult to do things that really are data hungry, like dialogue systems. Or training dialogue systems require dialogue turns and all that kind of thing. And that's been traditionally very hard to do. So maintaining multi-step interaction with the machine, all the interaction I've shown you is 1 or 2 step interaction. There's really no dialogue happening. Largely is question and answering and those kinds of things, right? And that's really hard to do. And I think interesting, clever ways are needed to scale this thing, to have a dialogue with a person, like, okay, what do you want? Do you want this? Do you want that? That kind of an engagement, which is naturally happening in NLP side. That's much more difficult to do. And the second part I wanted to mention is long context. So particularly when you have multimodal models, like the video work that I showed or the gesture work, context windows are still very small, right? So to do really long range understanding, keeping things in memory becomes challenging. And there, I think even it's not just NLP, it's also systems that need to be developed, which can handle large memories on these things. But there's also low-hanging fruit, and I think there's more work to be done on the subtleties of NLP. The fact that NLP is also about speech, it's also about intonation, it's about emotion. So consider, something that we really think about is machines taking care of the elderly at home or making their lives easier or simpler, right? There, the emotion matters. Can you recognize if a person is really happy, and can you speak in an excited way, or those kinds of very specific classic NLP things is something that is something which is to be explored more, and there is scope for some interesting work there. Again, if you think of robots interacting in an educational setting with children, this is going to be very important. No child would like to be with a person who's boring. So the robot which is interacting with the child, let's say for teaching material kind of thing, needs to have some expressibility, some emotion, some things. And I think there's more work to be done on that side. And on the other side, more on the technical side, I would say that understanding speech is also equally important. And a lot of errors in our systems happen because of not recognizing speech correctly. So the new developments happening in direct speech to speech language models, that line of work, which in some sense bypasses or directly starts working on speech, may be an interesting avenue for future researchers to do, because that is preventing deployment. So in a real setting, things are noisy and things are a little bit unstructured, and any improvement on that side, I think, will also have certain implications on improving these technologies. And this also is a progressing field. It's not just about wheel robots, or I showed a lot of manipulation work, navigation work is also where we've applied this, but even more interesting things are coming around the corner, like legged machines or legged robots, humanoids. These kinds of platforms are going to come, which are going to bring even more richness to this entire problem of communicating with machine. So with this, I'll stop and I'll say that clearly this is a team effort, and a lot of people have been mentioned on this slide, and there are, I think, even more. And they've been part of this activity, and this kind of system building is a team effort. And do want to acknowledge all my collaborators here, most of them, all the students and the research staff, and all the support at the lab level that we have in order to do this kind of work. And with that, I thank you, and thank you for this opportunity. And I really look forward to your feedback and any questions.
So there are no questions at the moment.
Yeah.
So there are no questions at the moment. Am I audible?
Yes. So okay,
Yes, sir.
then maybe we can close the session then. Is that fine?
Yes, sir. Thank you so much for the
Okay.
insightful lecture. Thank you, sir.
Thank you so much. I really appreciate, and it's a privilege to be here and to be interacting with all of you. Thank you so much. Really appreciate it.
Thank you, sir, for joining us today. Thank you.
Thank you.
Thanks, Jim.